Corney, and my mathematician is Thomas Bayes. So a little background about him. He was born in 1702 in London, England. And his father, Joshua Bayes, was a nonconformist minister, which basically meant that he was a minister that didn't conform to the practices and disciplines of the Protestant church in England at the time. So because of this, Thomas Bayes was educated privately because the institutions all kind of fell in line with the Protestant religion and their practices at the time. So little is known about like who his tutors were, educators were during his youth. But as he got older, he went to the University of Edinburgh because it was the only school in the area, I think this is in Switzerland, that would accept nonconformists, people who were nonconformists, and he was. So there he studied logic and theology, and then he followed in his father's footsteps and was ordained himself as a nonconformist minister around 1733. And then he tried to retire a little bit earlier in 1749, but was successful in 1752. So after retiring from ministry, they set out to focus on his theory of probability. And he did study logic at his university. So throughout his ministry, he was still interested in mathematics, but his main priority was to be a minister, so he couldn't really do much at the time in terms of actually diving deep into probability. But once he got out of that, his first recorded findings of what he was working on in probability was in the essay towards solving a problem in the doctrine of chances. And he did that like later on in life when he was older, and it was published after he died in Philosophical Transactions by the Royal Society, which was basically just like the fellowship of educated people, learned people who like came to promote the validity of newfound findings during the time and kind of discuss them. So yeah, he had very few published works because he started his he started actually diving deep into probability later on in life, like in his 50s, 60s, and a lot of his works were published after he died. So this is Bayes' theorem. Basically what it says is the probability of event A, and event A given event B equals the probability of B given A times the probability of A divided by B. It's a very easy proof, so I'm just going to do that and then give an example because I feel like the example kind of illustrates better what this means. So you have so I'm pretty sure we all know like that the and is the intersection of A and B. So if you have a Venn diagram, then you have A and B, this is where the and would come in. And so the probability of A given B has already occurred is this equation, which is, this is just a given symbol. B equals the probability of A intersect B, which is this, divided by just the probability of B, which is the same thing as probability of B given A equals the probability of A intersect B divided by the probability of A. So since these two are the same, we can divide, or we can multiply this A on both sides or whatever. And then this would be times the probability of A equals the probability of A intersect B. So since this, the probability of A intersect B equals this, we can substitute it in it. We can substitute this in for this, and then this would equal the probability of A given B equals the probability of B given A times probability of A over the probability of B. So that's basically just the proof of it, but I feel like an example would be a little bit better. So I'm just gonna erase this. Quick example. So if we have this is hard. Okay, so the example I'm gonna do is there's a class, and there's one, I guess, event would be whether you passed or failed, and another one would be whether you're male or female. So this would be pass, fail, female, male. The total in the class is 100, or oops. The total in the class is 100. There are 70 people who passed, 30 people who failed, 50 who are female, 50 who are male. And then the intersections of these are all just like numbers, just is 40, 10, 30, 20. So the probability of pass is 70. And also probability is between 0 and 1. So just divide this by 100. The probability of pass equals 0.7. And then the probability, let's say that you're female in the class, is 0.5. And you look over here out of all of it. So then the probability that you pass and you're female is 0.4. And we get this from right here, pass and female. So then the probability of that you pass given you're female equals, and we're going to use this equation, the probability that you're female given you pass times the probability that you pass divided by the probability that you're female. So in order to get this part, I wish I had erased that. But I'll start here. It's going to be, this part is going to be the probability that you're female and you pass equals the probability of pass and female divided by the probability that you pass, which is both of this that we already got is 0.4 divided by the probability that you pass, which is 0.7, and that's about 0.57. So now that we have this, we can put it into here, which is going to be, this part is 0.7 or 0.57 times the probability that you pass, which is 0.7 divided by the probability of you being female, which is 0.5. So that equals 0.8 or 80%. So basically this number is, instead of it being the whole total, you're looking at this is the total, and 80% of the people, or people who are emailing past this line, it would be 80% of that. So
Say that again, 8% of what?
So instead of it being and out of the whole total, it's just, you're just looking at this line or these numbers. And so you kind of treat this as the whole total instead of the 100. And when you look at it this way, the 40 would be 80% of the 50. So that's kind of like how it comes together, because it looks a little bit weird when it's just probability of A, probability of B. But yeah, so that's that. So the controversy with Bayesian statistics is that there's kind of like a debate, I guess, in statistics even now, which is Bayesian statistics versus frequentist statistics. So basically the difference is with Bayesian statistics, it's very inference-based, and it's basically, say you're doing an experiment. Before you do the experiment, you have a set of beliefs of what the data is gonna look like. You carry out the experiments, and then you adjust the probability based on the data. So you basically just adjust your beliefs, and it's a little bit more subjective because you already have an idea of what the data is gonna look like, or the probability of what the data is gonna look like. But with frequentist statistics, there's no prior beliefs about what the data is gonna, or what the probability of the data is gonna look like. You just carry out the experiments and you come to a conclusion based on what you gathered, which is more objective since you like come into the experiment with a clean slate. So frequentists argue that there's really no need to have a belief before you go into the experimentation, because the data is not going to change whether you have that set belief in the beginning or not. So it's really not necessary, but sometimes it can be, and that's why it's still like up for debate today. Like I know our university goes more with the frequentist side of it, but I know other universities, they teach their statistic classes with Bayesian statistics. So it's not one is better than the other, it's just preference. So yeah, and that is the end of my presentation.